Okay, let's look at section 1.2, homomorphisms and subgroups. So you recall, in the broadest sense, that an isomorphism between two mathematical structures is a one-to-one and onto mapping, a bijection, that preserves a structure. Now, it depends on what this mathematical thing is as to what its structure is. In a semigroup, we'll initially set definitions up for semigroups, and a semigroup, which encompasses groups and monoids, but the structure is the binary operation. In a vector space, the structure is linear combinations. So two vector spaces are isomorphic over the same scalar field. If there's a bijection, one-to-one and onto mapping, from the vectors of one to the vectors of the other, that preserves linear combinations. In a graph theoretic graph, the structure is adjacency. So two graphs are isomorphic if there's a one-to-one and onto mapping, bijection, that preserves adjacency. So here, it's the binary operation that gives the structure of a group. So we'll define homomorphisms, isomorphisms, and some related Latin terms. Definition 1.2.1 starts again with semigroups. Okay, so that means they start in the general setting. That means the following applies to groups in particular, which is our main focus. So let G and H be semigroups. A function f mapping group G into group H is called a homomorphism if f of AB equals f of A, f of B for all A and B in group G. Now, there's a little bit more to this than meets the eye. There's an implied binary operation between A and B. They're elements of group G. F maps elements of group G. So there's a binary operation between A and B, so we're using multiplicative notation. It's the binary operation in group G. On the right-hand side of this equation, there's a different binary operation, same multiplicative notation though, because f of A and f of B are elements of group H. So there's an understood binary operation between these two elements of group H. It's the binary operation of group H. So it's a touch more involved than it might appear on the surface. We won't really deal with the binary operation so much notationally. We'll just stick with the multiplicative notation. A one-to-one or injective homomorphism is called a monomorphism. An onto or surjective homomorphism is called an epimorphism. A one-to-one and onto or bijective homomorphism is called an isomorphism. Maybe a little bit more before some commentary on that. If groups G and H have an isomorphism between them, and they're said to be isomorphic, and we use a standard notation to represent group isomorphism. A homomorphism from a group to itself is called an endomorphism, and an isomorphism of a group to itself is called an automorphism of that group. So there's your dose of Latin. These terms, one-to-one and onto, really, these are more terms from the analysis realm. I'm sort of from the analysis realm, so I prefer those terms. But one-to-one and injective means the same thing. Onto and surjective means the same thing. And the algebra world seems to be drawn more to the terms injective and surjective, just FYI. Whatever, I'll kind of mix the two up, and oftentimes I'll actually use both of them just to be sort of bilingual in that sense. Now, what we've got here that's of the most central importance in what follows is the idea of homomorphism, the idea of an isomorphism, and not so much now, but eventually the idea of automorphisms of a group. So really homomorphisms and isomorphisms for now, with a side order of automorphisms being of some interest. We'll run across these other terms. Endomorphism will pop up a few times, but primarily it's homomorphisms and isomorphisms that matter. If f maps group G into group H, G maps group H into group K, are both homomorphisms on semigroups as given. Then the claim here is the composition is also a homomorphism. So there's something to be shown there, that the binary operations are preserved through the composition of these two maps. We'll abbreviate this G composed with F simply as a GF, as if this were some type of multiplication as well, some type of binary operation. It will be. We'll make groups out of automorphisms in particular down the road. But beware, in this setting of talking of homomorphisms, we may exclude the little circle that indicates function composition. So we make a claim that compositions of homomorphisms are homomorphisms. Likely you did this in senior level algebra. Similarly, compositions of monomorphisms, epimorphisms, isomorphisms, and automorphisms, all those morphisms we just saw, are respectively mono, epi, iso, and automorphisms. One-to-oneness, for example, is preserved when we compose two one-to-one mappings, we get a one-to-one mapping. When we compose two injective mappings, we get an injective mapping. Standard results likely from either senior analysis or maybe even math reasoning for you. You're probably familiar with the fact that group homomorphisms map identities to identities and inverses to inverses. If we weaken the structure a little and consider not group homomorphisms, but a monoid homomorphism, so these are the ones that have semigroups with an identity, but not necessarily inverses. A monoid homomorphism might not preserve identities, might map the identity to something else or something else to the identity, as is to be shown by an example in exercise 1.2.1. We're primarily here to talk about groups. So the fact that homomorphisms map identities to identities and inverses to inverses of groups, that we'll use quite often. An example of a homomorphism, let G be the integers and let H be the integers mod M. And we'll deal with the integers mod M in more detail later. For now, the integers mod M is a group of order M, so it's a finite group. You're familiar with arithmetic mod M. Strictly speaking, the elements of the integers mod M are equivalence classes of integers. We'll denote an equivalence class by putting a bar over it. X bar represents the equivalence class containing X. In this case, it'll be integer X. For example, if we look at 0 bar, that'd be the equivalence class of all integers which are equivalent under congruence mod M. So 0 bar contains 0. It also contains all integer multiples of M, because all integer multiples of M are also congruent to 0 modulo M. So if in your senior level algebra class you dealt with integers mod M, maybe as 0, 1, 2, up through M minus 1, well, the structure is the same, but notationally we'll represent those elements as 0 bar, 1 bar, 2 bar, up through M minus 1 bar. And again, more details of this in a couple of sections. So what we're doing here with F is we're mapping the integers into the integers mod M by taking an integer X and mapping it to the equivalence class in Z sub M, which contains X. For example, 0 is mapped to 0 bar. M is also mapped to 0 bar. M is in the same equivalence class as 0 modulo M. 2M is mapped to 0 bar. And of course, I've got arguably some ambiguity. 0 bar is the same as M bar, is the same as 2M bar. They're all the same equivalence class. But we're doing a mapping from the integers, which is infinite, into Z sub M, which is big time finite. The claim here is we have a homomorphism, so the binary operation of addition in the integers is preserved in this mapping, and the binary operation in Z sub M is addition modulo M. So no surprises in that claim that it's a homomorphism. Really no surprise in the idea that it's not one-to-one. For example, 0 and m are both mapped to 0 bar, as is a bunch of other things. It is onto. This homomorphism F is onto every equivalence class from Z sub m, of course, is the image of something from Z. So F is an epimorphism. On down the road, we'll call it the canonical epimorphism of the integers with the integers mod m, and we'll generalize that idea when we look at cosets and normal subgroups and quotient groups. And we'll have a canonical epimorphism at that stage. That terminology and that behavior best illustrated really by this example here. So this is a good example in terms of canonical epimorphisms and some things to follow. If A is an abelian group, we can define the mapping from A to itself, defined by mapping A to A inverse. This is an automorphism of A. Notice commutativity is required. If memory serves, I suspect it's to deal with preserving the binary operation when that inverse gets in there. AB inverse is not A inverse B inverse. You'll recall AB product inverse is B inverse, A inverse. And you even see that kind of behavior with matrix multiplication. And I suspect that causes a little bit of a problem with this mapping if we don't have the commutativity. If we take G mapping A into A defined as A is mapped to A squared, then this is, again, it's a mapping of A into itself. It's onto, it's not one-to-one, it's an endomorphism of group A with itself. Another example with integers mod m and integers mod mk. We could map with function f an equivalence class in Z sub m to the equivalence class kx. Let m and k be given natural numbers, not 1. I want to deal with addition mod 1, so we just get a trivial group out of that. But if we'll take the mapping that takes x bar, an equivalence class in Z sub m, maps it to k times x bar, equivalence class containing kx, this is another example of a monomorphism. So we've got one-to-oneness in that mapping, and it's a homomorphism. Okay. Here, these definitions might be familiar to you from an analysis setting, at least in part, these ideas of images and inverse images. What's different here is we're in our setting, and our setting is the functions for now. They're homomorphisms between groups. So let F be a homomorphism mapping group G into group H. The kernel of F is defined to be the elements of G such that under this mapping F, they're mapped to the identity of H. You're familiar with the idea of a kernel in the setting of matrices as linear transformations. The null space of a matrix is a collection of vectors that under that matrix are mapped to the zero vector. Well, a zero vector in some sense is an additive identity in the appropriate dimensioned vector space. And so the null space of a matrix is certainly intimately related with this idea of a kernel, the kernel of a homomorphism between groups. So there's your additive identity, just as we'd expect to see zero vector as an additive identity in a vector space. If A is a subset of G, then the image of A, here we got A as a set of elements from the group. The image of A is denoted F of A, and it's simply all the F of A's we get out of the function by plugging in the elements lowercase a of the set capital A into the function. Symbolically, it's this. So it's what comes out of the function. You might want to call it the range of the function even. The set F of G, so here we're taking the image of the whole group G, might think of that as the domain of the function F. F of G is called the image of the homomorphism, is denoted image of F. So for homomorphisms, we might have an interest in images, and we'll definitely have an interest in kernels. If B is a subset of H, so now we're looking over here, the output of the function, if you will, the codomain maybe. So we're taking B as a subset of group H, set, not necessarily group, subgroup we haven't defined yet, but it's coming. If B is a subset of group H, the inverse image of B is the set F inverse of B. It's the G's, lowercase g's in group capital G, that are mapped by F into set B. A little bit more of that in a second. The identity mapping of a group into itself, we'll denote that with an I for identity. Though the Hungerford book will commonly denote this as 1 sub G, 1 for identity sub G because it's the identity on group G. So we'll see in the book, and I'll put some of it in the notes as well to get used to the ideas. We'll see an identity mapping on group G or other structures. The identity mapping indicated at a 1 sub G, say, for identity on G, 1 sub H for identity on H, and so forth. Now about this inverse image stuff, of course, that's not to be confused with an inverse function. If we were to consider the mapping of the integers into the integers as f of x equals x squared, this is not one-to-one. It doesn't have an inverse. I can still talk inverse images though. And if I ask you what's the square root of 9, well, there's two choices. There's a principal square root, 3, and then there's another square root, -3. So plus or minus square root, that's not a function. When you say the square root of a positive real number, you mean the positive square root. But we can still talk inverse images, even though the inverse function of f of x equals x squared doesn't exist, not a one-to-one function. But inverse images still make sense. So we don't have to worry ourselves over one-to-oneness or anything to talk inverse images. A note, we'll use this in some of the proofs coming up. This is stated on page 5 of Hungerford. So this is sort of considered some remedial stuff. And I've stated things in terms of one-to-oneness and on-to-ness versus injective and surjective. But our setting is F maps set A into set B. We're considering sets. So it's this one-to-one and on-to-ness that's of interest. There's no structure to a set. There's no binary operation or anything like that. So you don't talk about isomorphisms of sets. Sets are just collections of things. They don't have necessarily any structure to them. So F maps set A to set B, G maps set B to set C. So we can do some composing here because of the codomain and the domains as given. If F and G are one-to-one, injective, then the composition G composed with F is also one-to-one. If F and G are onto surjective, then the composition is also onto surjective. So compositions of one-to-one functions are one-to-one, compositions of onto functions are onto. Probably you've encountered this before, so something you may have encountered or not, maybe not, but useful in what we're about to do. If the composition is one-to-one, then the function f in the composition G with f is one-to-one. So the second function in the composition is one-to-one if the composition is one-to-one. And the first function in the composition is onto if the composition is onto. So these deal with inputting single functions with certain properties. These deal with a composition having a certain property. These deal with conclusions of the compositions. These deal with very specific conclusions of the functions in the composition. So we'll take that as given background information. We've got bigger fish to fry than that. Theorem 1.2.3 says, let F map group G into group H be a homomorphism of groups. Then F is a monomorphism, injective, one-to-one. If and only if the kernel of F consists only of the identity element of G. Remember, we're using E sub G to indicate identity elements from group G. And secondly, F is an isomorphism if and only if there's a homomorphism denoted like this. Let me read it F inverse. Of course, it's going to be the inverse of this mapping F. I'm sorry, did I read that correctly? F is an isomorphism. If and only if there's a homomorphism F inverse mapping H back to G, such that the composition of F with F inverse is the identity on H, and F inverse composed with F is the identity on G. And you can see where these particular functions map. See, if we had this particular composition, this would first act on elements of G, and then act on elements of H and send them back to G. So the identities on the appropriate groups make sense. Let's look at a proof of that. Okay. All right. So let's prove this you've seen before, I'm sure, in senior level algebra, that a homomorphism is one-to-one if and only if its kernel consists of the identity. And you got some results related to that, I think, concerning matrices and null spaces as well from linear algebra. All right, so if F is a monomorphism, it's an if and only if result. Let's look at that part. If F is a monomorphism, then the meaning of monomorphism is a one-to-one homomorphism or an injective homomorphism. If A is in the kernel of F, then F of A is the identity in H, and that's what it means to be in the kernel of F. You're mapped to the identity, in this setting, the identity of group H. But we know homomorphisms map identities to identities. So F of E sub G, the identity in G, is mapped to E sub H, the identity in H. That's to be established in exercise 1.2.1, property of homomorphisms between groups. Probably you've done that before. So we've got A in the kernel of F, we've got F of A equals E sub H, and we know necessarily that F of E sub G equals E sub H. But we've got ourselves a one-to-one mapping, an injective mapping. So if we get E sub H out of mapping F, when we put both A and E sub G in it, F of A equals F of E sub G, the one-to-oneness tells us element A must be the identity. So if we have an element of the kernel, then it must be the identity of G, and the kernel of F consists only of the identity of G. So one-to-oneness, monomorphism, implies kernel is the identity of G. Okay, let's look at the converse of that, if and only if result. Now suppose the kernel of F consists only of the identity of G. Suppose F of A and F of B are equal. We're trying to show one-to-oneness. We want to draw a conclusion, and here it is down here that A equals B. So suppose a kernel of F is the identity of G, and F of A and F of B are equal. Then E sub H would be F of A times F of B inverse. Remember, F of A equals F of B, so F of A inverse is F of B inverse. We're in a group, no problems there, so all these inverses exist. Exercise 1.2.1, and we've commented this previously. For a homomorphism, F of B inverse is the same as F of B inverse. Symbolically, I can take inverses in and out of homomorphisms, just as I can, by the very definition of a homomorphism, a product of F's is F of the product, if you will. So by exercise 1.2.1, we can get that inverse inside. Definition of homomorphism lets us write this product. By the way, quick little question. Where's this product? What's the binary operation between these two elements? F maps us into H. The binary operation must be the binary operation from group H. So definition of homomorphism produces this. Here, between A and B inverse, by the way, the binary operation is the binary operation in G. F takes in elements of group G. So what we've got is E sub H, the identity in H, equals F of AB inverse. Well, there's something that's mapped to the identity of H, so there's something that must be in the kernel of F. But we've assumed the kernel of F consists only of the identity in group G, only of E sub G. So this AB inverse must be E sub G, and multiply both sides on the right by B, simplify, and we get A equals B. So we've assumed F of A equals F of B. In this setting, we've drawn the conclusion A equals B. that gives us that this function f must be 1 to 1, and that was the claim. Back to the notes, dealing with subgroups of a given group. Let G be a semigroup and H a non-empty subset of G. If for every A and B in H, we have AB in H, H being a set, then H is said to be closed under the binary operation of G. So closure of a set of elements under the binary operation. Let G be a group and H a non-empty subset of G that's closed under the binary operation of G. If H itself is a group under the binary operation, along with this closure property, then H is called a subgroup of G. So to show that H is a subgroup, we need to worry about closure first. We need to worry about identities. We need to worry about inverses. We need to worry about associativity too, but associativity is processed in the sense that, hey, the binary operation will be associative on all of the elements of G, and H is a subset of those elements. So we'll have associativity for the binary operation applied to elements of H as well. We use the standard notation, as given here with a less than sign, to indicate H is a subgroup of G. For a given group, the trivial subgroup is a group that consists just of the identity. Another obvious subgroup of group G is G itself. But H is called a proper subgroup if it's neither the trivial subgroup nor group G itself. So proper subgroups we're primarily interested in when we say subgroups, but the term subgroup allows for these other examples as well. Consider, say, the integers mod 6. The elements of which, as we commented earlier, is 0 bar, 1 bar, up through 5 bar. These are equivalence classes. They actually contain infinite number of integers. This represents the set of all integers congruent to 0 mod 6. This represents all integers congruent to 4 mod 6, for example. And we do the addition in this collection of equivalence classes the usual modulo 6 way. So a couple of subgroups are 0 bar and 3 bar. We got closure. Sure, add any two of these together. We get something else in there. 3 bar plus 3 bar is 0 bar. So we do have the closure. We'd have to have the identity to have a subgroup. Here we've got the identity and we've got closure, and associativity is inherited. You good with inverses? Yeah, 2 bar plus 4 bar is 0 bar. So 2 bar and 4 bar are additive inverses of each other, these additive groups. So here's a couple of examples of proper subgroups of Z sub 6. You know, it's no coincidence that we've got a group of order 6 with a subgroup of order 2 and a subgroup of order 3. In the integers, let n be any natural number other than 0. Arguably 0 is not a natural number to start with, but take n to be a positive integer. Then n times z, all multiples n of the integers, is a subgroup of the integers. For example, we could take all even integers. That's where n equals 2. The set of all even integers under addition forms a group. Closed, additive inverses, associativity, of course. Funny thing, as you're asked to show in exercise 1.2.7, n times z is isomorphic to z itself. Kind of an odd, well, if you're really used to finite groups, that's an odd type of behavior, because nz, when n is greater than 1, is a proper subset of the integers, yet we still get them as a group to be isomorphic to each other. Yeah, that won't be happening with finite groups. We've got a proper subset and a proper subgroup, but this group nz is isomorphic to the integers themselves. Odd, but funny behavior for infinite groups. In the symmetric group, S sub n, as is shown to be shown in exercise 1.2.8. Take the symmetry group, S sub n. We're going to take the subset of that of all sigma in S sub n such that sigma of n equals n. So it's a permutation on the symbols 1 through n that fixes that last symbol, fixes the nth symbol. Permutations of 1 through n, which leave the symbol n fixed. This is a subgroup of S sub n, as to be shown in the exercise, not a surprising result. Also, since you've fixed n by these particular permutations, you've kind of effectively eliminated it from any sort of algebraic role. And you're really effectively looking at symmetries on the symbols 1 through n minus 1. Effectively being, the math word being isomorphic. So this subgroup of S sub n is actually isomorphic to the group S sub n minus 1. It's not the group S sub n minus 1, it's isomorphic to it. It does involve permutations on the symbols 1 through n with some added details. So S sub n minus 1 deals with permutations on the symbols 1 through n minus 1, which this effectively does, but technically they're not the same group, they're isomorphic groups. If F maps G to H is a homomorphism of groups, then the kernel of F is a subgroup to be shown in exercise 1.2.9a. Straightforward, probably did this in senior level analysis. So kernels are subgroups, kernels of homomorphisms are subgroups. This will play a big role a couple sections down the road when we start looking at cosets, normal subgroups, and quotient groups. Then this idea that the kernel is itself a subgroup will certainly have a role to play. A little bit of a comment about automorphisms of a group. Remember, an automorphism of a group was an isomorphism of the group with itself. If G is a group, then the set out G, the set of all automorphisms of G with itself, is a group under the binary operation of function composition. So we start with group G, then we look at all automorphisms of group G. That would be all isomorphisms of G with itself. Introduce the binary operation of function composition. We stated upstairs that a composition of injective functions are injective, a composition of surjective functions are surjective, so a composition of bijective functions are bijective, or one-to-one and onto. So when I take two automorphisms and compose them, I get another automorphism, in other words. So we can actually make a group out of the collection of automorphisms of a given group. This we'll probably touch on really just to illustrate the ideas. Example 1.2.15 gives some details on this. When in field theory, we look at Galois theory in chapter 5, that'd come in Algebra 2, near the end, more than likely. These ideas of automorphism groups play actually a fairly fundamental role. All right, let's look at theorem 1.2.5, and then maybe we'll take a little break. It says, let H be a non-empty subset of a group G. Then H is a subgroup of G if and only if AB inverse is an element of H for all A and B in H. So this gives us a way to check, if and only if, to check to see if we have a subgroup. It's closure under this particular manipulation here. So let's look at the proof of that. I guess I failed to go through the proof, the second part of theorem 1.2.3, where we were dealing with compositions. The note 1 that we had stated earlier plays a role there. Sorry about that. So I'll leave that hanging, I suppose. Let's do theorem 1.2.5, this thing about subgroups. Okay. So the claim is we've got a subgroup if and only if for any A and B in H, AB inverse is in H, with the assumption that H is nothing more than a non-empty subset of G. Okay. Suppose AB inverse is in H for all A, B, and H. We want to show H is a subgroup. There's a conclusion down there. So there's the implication in one direction. H is non-empty, so there's something in it, call it A. take, in this A-B inverse thing, take A to be A and take B to be A as well, knowing that all such products are in H for elements of H, and knowing that A is in H, we can do that. So take A inverse, that's the identity. That must be in H by the assumption that we're working under here. So the identity is contained in H. So all we know is the identity is in H. I'd like to throw around the word monoid now, but we haven't established closure yet. So once we establish closure, then we can draw the conclusion of a monoid. For any B in H, we have, okay, here's what we know is in H now. We've assumed that that B is in H, and we've shown that E is in H. So let's take A equal to E, B equal to itself, and we can draw the conclusion that E B inverse, the identity B inverse or B inverse itself, is in an H. So now we've shown if B is in H, then the inverse of B is in H. We're still not done. We haven't addressed associativity, and we haven't addressed closure. So if A and B are in H, we know that B inverse is in H. We just showed that, so it's A inverse for that matter. So if we'll take another product of this form, I'm going to let A equal A, and I'm going to let B equal something else in group H, and let it equal B inverse. So we get A, B inverse. Inverse, that's a product of this form of things known to be in H. B inverse inverse is B itself. So A, B inverse inverse is A times B. We know A, B is in H. We just took A and B to be in H and showed their product is in H. So there's the closure. Closure under the binary operation as we just defined. Actually, what this closure really establishes is that we have a binary operation on H itself. A binary operation takes two elements of a set and gives you back something in the set. Yeah, we're good. We take two things in the set H and we get back something in the set H. So we've shown the identity is in H. We've shown for anything B in H, its inverse is in H. We've shown closure, associativity. Usually just say associativity in this subset is inherited, as we mentioned earlier. Hey, if you got associativity on the elements of G, the elements of H are elements of G. H is a subset of G. So we'll have associativity on all elements of H. It is inherited from the bigger group G. So associative binary operation, that right there gives you a semigroup. Identities are there. That semigroup, in fact, is a monoid. Inverses are also there. That thing is actually a group. That is, H is a subset of G, which is a group itself. So H is a subgroup of G. The other direction's a piece of cake. If H is a subgroup of G and we take anything in H under the assumption that H is a subgroup of G, well, the inverses of these things must be in H, part of the definition of a group, in particular B inverse is in H. And we've got A and B inverse in H. It's a group. It's closed under the binary operation, so A, B inverse must be in H as well. So this theorem 1.2.5, this will be dealing with quite a bit. So I'm not good at remembering these things at all by their numbers, but I'm going to remember this one. We're going to use this thing to establish that a collection of elements is a subgroup. This we'll use quite a bit. So let's take a break there, and we'll come back and look at generators of a group and finish up section 1.2. So have a nice day. I'll see you shortly, hopefully, in the remainder of section 1.2. Bye-bye.